Okay, okay. So how many have seen vectors maybe in their physics class? The physics class they've taken. How many are a little bit, how many are familiar with vectors, or at least have seen them in other places? Okay, Binyam, Nema, Christopher, Robin, John, um, quite a few of you. Marvelous, Ryan. Okay, and you know, of course, there you go, Eric. I hear you. Vectors represent, well, a vector has a length and a magnitude, and so we can model velocities and forces and tensions and wires and things like that with vectors because those follow that's just because. Okay, a vector has a magnitude and a direction, just like forces and velocities and tensions do. So it's important that we understand the mathematics of vectors, and that's what section 9.2 is about. And they always usually have an author here that talks a little bit about things, but let's just go ahead here, and I'm going to give you a little bit of a guided tour of section 9.2. So in the book, like when you write a vector, in this course, you want to write a vector with an arrow above it. Now, I know there are other notations for vectors, but this is the best notation, and it's the one that I would like you to use for this course. So a vector should be written with an arrow over it. Believe it or not, other notations, like sometimes I've seen vectors where they have like a hat over them. I don't know if you've seen that notation. They'll have like a V with a hat over it. But yeah, but the thing is, in statistics, well, statistics, a hat means an approximate means hold on, an estimate, right? So we have to be a little bit careful with our with the notation, and this is actually the best. So right, with the linear least square sign, exactly, Binyam, like in linear algebra that you learned, an approximate solution, so to speak. Okay, so going into the book here, these are equivalent vectors in figure 1. These are equivalent vectors. Vectors v and u are equivalent. Why are they equivalent? Well, they have the same direction and they have the same magnitude. So those are equivalent vectors. Now I'm going to give you a guided tour. Let me know if you have any questions as I move along, okay? Okay. So how do we combine vectors? Well, vectors can be combined. Okay, so in figure 2, you have a vector AB and a vector BC, and the vector AB, you start at A and go to B, and that's denoted here. I wonder if I can make that. Yeah, that notation means you're starting at point A and going to point B. That's the direction of the vector from A to B. And looking in figure 2, if you add the vector AB and the vector BC, that is equivalent to the vector AC, because your starting point and ending point are the same. And you add vectors tip to tail. You can add vectors tip to tail, and that's what they're doing here in figure 2. All right. And that's the definition of vector addition. So the figure shows it very nicely. But here's another little figure, figure 3. Are there any questions on figure 3, how like the u and v, u plus v equals u? Well, they're graphically showing you the vector addition. Are there any questions on that? And you can think of it in terms of like forces. If you have a force that's a vector u, that's a force, and a vector v, that's a force. If you have two vectors, one pushing in the direction of u with that magnitude, and another force pushing in the direction of v with that magnitude, and the length of the vector dictates the magnitude, then the sum of those forces would be equivalent to the force u plus v. Okay, how many learned that in physics? How many maybe you've seen that in physics? That kind of, okay, Namath's seen it, and you know, it's helpful. Eric's seen it, sure. But you know, it's helpful sometimes to think of, you know, to try to tie these concepts together. Okay, well, moving on here, you know, so I'm not going to go over every little thing. But, you know, you can multiply a vector by scalars. So here in figure 7, you have a vector v, and what they're doing here is they're going 2 times v. That's just doubles the length of the vector. Doesn't change the direction, it just doubles the length of it. A half times v will make the vector change the magnitude, so it's only half as long. Negative v would reverse the direction of the vector v. Okay, so taking the vector v and multiplying it by -1 reverses the direction. And, you know, are there any questions on figure 7? All right, we're just learning some basic things here. Okay, I think you can manage. Okay, now vectors have components, okay? Vectors have components, okay? So, depending on what your coordinate system is, your vector A could have coordinates A1, A2, or A1, A2, A3, as shown in figure 11. The coordinates are called the components of the vector A. And the way you write the vector A is using the bracket notation that you see here. Okay, that's one way to write vector notation. Okay. Are there any questions on that? Okay, I'm giving you a guided tour here. Okay. Okay, so let's keep moving here. Here they show representations of the vector A. It has components A1, A2, A3. And again, you know, both of these vectors, I mean, traditionally we think of the vectors coming out from the origin, but both of these vectors have the same direction and magnitude, so they're equivalent vectors. You know. Okay, in example 3, they want you to find the vector represented by the directed line segment with initial point given here, 2, -3, 4, and terminal point given by -2, 1, 1. And all you do is to do that, you just subtract the components. You subtract the components of the vectors, and that's how you find the corresponding vector AB. Okay, and that was, I mean, graphically that would make sense, but that's how vector subtraction is defined. Okay, and it's not hard to see that's true. Okay, so, and if you want to find the length of a vector, with components A1 and A2, you just take the square root of the sum of the squares of the vector. Okay, that's what you do. I mean, that hopefully makes sense. Hopefully that makes sense. If you, let me see here. Let me go and share the whiteboard for a moment. Okay, maybe I'll put it in black here. Okay, so let's say you had a vector like this, and the vector goes from the origin to the point 3, 4. Okay, and this is vector A. And it has coordinates 3, 4. Well, the magnitude of the vector A is just the sum, square root of the sum of the square of the components. Okay, and that would, I mean, the magnitude of A, that's the length of A, and that would make sense, because if you know, hold on here, if you do this and you form a right triangle, what is the magnitude of A? You know, the magnitude of A, of course, is this distance, but that distance is what relative to the right triangle? That distance would be the distance of what? It would be 5. What do we call that?
The hypotenuse.
The hypotenuse. That's right. That's right. Good, Marvelous. Good, Christopher. It's the hypotenuse. And we know, what special theorem are we really using here? What theorem are we using?
I mean, it's the distance formula, but it's also Pythagorean.
Yeah. Think that it's just the Pythagorean theorem. That's right. That's right. And so indeed, you know, that's the square root of 25, and that equals 5. Okay. And of course, you know, our vector A is 3, 4. But, you know, if we wanted to be very clear, you know, hey, if we take 3 and subtract 0, subtract the x components, and subtract the y components, we get 3, 4. So remember, you saw how to find the components of a vector going from one point to another point. You just subtract I should say you subtract the x coordinates and the y coordinates, and those form your new component. Those form your components of your vector going from an initial point to a terminal point. And does that make sense based on the little picture here? I'm just trying to, you know, they give these definitions, but I always think it's helpful to see an example, to look at a little example, and then the definitions are clear. How many find that to be the case too?
Yeah, I mean, it's the vector floats, so this is like a series of directions, not of coordinates, which is
right. Okay, and thank you everybody for your input there. All right, well, let me take this off then. It's on the recording. And let me go back to the thing here. So I'm thinking maybe I'll give you a little time to work on that section 9.2 assignment. But you know, these definitions now, the length or the magnitude, you know, they all make sense. They make sense, intuitive sense, you know. And you know, operations of vectors. In example 4, they talk about you know, adding vectors, subtracting vectors, and all that. And you know, I think hopefully that'll make some sense to you intuitively. And finally, we get to some properties of vectors. You know, here are properties of vectors. They're very intuitive, very intuitive. But let me see here. Is there a question? One moment. Okay, Christopher mentions about a class Discord website. I guess that's a chat video place for people to talk about things and you know, maybe help each other. That's great. Thank you, Christopher. Let me see. Let me go a little bit further down here, a little bit further. So also with vectors now, how many have seen these vectors maybe in a physics class? The IJK vectors. Absolutely, absolutely. Yeah, and you know, this gives us then the ability to write vectors using a different notation. So, like for instance, well, there in Figure 17, they show the standard basis vectors for 2-dimensional and 3-dimensional space. Okay, so I always like to see pictures. Helps me. All right, there's Figure 17. And are there any questions so far? All right. Well, and then here's what's very nice too. You know, you have here 2 ways to write now a vector. You can write it in the component form on the left. The vector 1, -2, 6 would be equivalent to I minus 2j plus 6k. Okay, so it's 2 ways to write a vector, and you know, it's very handy. It's very handy to be able to have that way too. So, like for instance, okay, in example 5, they say, all right, well, if the vector A equals I plus 2j minus 3k, and the vector B is 4i plus 7k, express the vector 2a plus 3b in terms of I, j, and k. And they show you that below. Okay, and it's like combining like terms. You combine the I vectors, the j vectors, and the k vectors to get your final vector. Okay, I mean, are there any questions so far? All right. Well, let's look at one more thing here. A unit vector. So sometimes you want to take a vector and you want to normalize it so it has length 1. And all you need to do is to divide that vector by its length. And then the resulting vector will be a vector, the vector u will have length 1. Okay, and they show this here. In order to verify this, okay, they multiply a vector, well, they define a vector the magnitude of the vector u is equal to the magnitude or the length of the vector u. I'm going to use length because we're in calculus, multivariable calculus. The length of the vector u is equal to the length of the c times a. But the length of c times a, you can factor the scalar out, and the scalar is equal, the scalar is defined as 1 over the length of a, and so you get a length of 1 for the vector u. Okay, so it just, and again, you know, it helps to do some problems to give you a feel, but that's an intuitive feel for that concept. I tend to like examples, working examples, but are there any questions on that? All right, so we're gonna do in our next class, we're gonna get into some applications, okay, of vectors. It'll be, we're gonna cover other things too, but I do want to do an application with you, but I'm gonna hold off on that. We'll do that on Thursday's class. And let me go ahead and stop the recording.